Now, let us go through an example problem on how we can design a post tension deep beam. What I have here is a you can see that you have about girder dimensions are given here, which is subjected to 2 heavy concentrated load of 4000 kilonewton, and you can see the load is applied from the edge of the beam at a distance of 3500. The dimensions of these beams are given as width is 500 and your depth is, you can see, 4000 or 4 meter. It is really a huge transfer girder, and we are taking a concrete cylinder compressive strength of 30 megapascal and a reinforcement yield strength of 500 megapascal, right. Now, the yield strength of post tension strand is taken as 1860 megapascal, and you are stretching it up to 75% of the initial pre-stress, right. And we are assuming that the losses are going to be about 25%. So, these are the input dimensions. Now, we need to design this beam, particularly we need to find out what should be the amount of post tensioning reinforcement that is required. In addition to that, we need to put also some horizontal and vertical reinforcement as per the code provision, so that the struts and ties are not going to fail in an abrupt manner. Let us look at step by step. So, we know that this ratio, if you can see shear span to depth ratio, clearly it is less than 1. So, it is going to be acting like a deep beam. So, we know that we have to use strut-and-tie model. So, let us see how do we construct strut-and-tie configuration, right. So, these are the dimensions. Now, I am going to assume, as you can see, the ties have to be either horizontal or vertical, and just below the point load we need to also have a strut. These are all the broad guidelines we know. So, let us look at it now. So, I am assuming that I am going to have some nodes below the reaction point and the load application point. Then I am going to have struts that will be forming. The light grey color is strut, again this is strut, this is also strut, this is also strut. Now, at this joint again you need to also have some ties, and we are assuming that the dimensions of this struts and ties is, strut is dA and the tie width is HA, right, and I am taking only half because we are measuring to the center line, right. Similarly here, so I am measuring only to the half, right, half. So, we need to of course find the dimensions of HA and dA. So, let us see how do we do it, but this seems to be an efficient strut mechanism that you can see, because the load has to transfer to the support like this. So, we oriented the strut like this. Again, to balance the loads, I need to have a strut-and-tie here if I take a section like this, right. So, this is a very efficient truss mechanism that we have formed. So, you are going to have basically a diagonal compression strut and a straight strut. I am calling that a C and D. D is a inclined strut, diagonal compression strut, and C is your straight strut. Then you also have a tie element, and they are making an angle alpha. Of course, we need to find out what that angle alpha and so on, but this is the basic configurations, and this is your node regions. So, these are your node regions, nodes. Okay. All that highlighted in blue color are all node regions. The green color one is a tie, and the grey color ones are the struts. Now, let us look at the first estimate the geometry of the strut-and-tie model, and so that means I need to find out what is the dA and HA. Let us look at how do we do that. It is basically what we are saying, before the forces in the strut-and-tie can be calculated, first we need to estimate the height HA over which the tension reinforcement I need to provide, and also the depth dA for the top compressive strut. So, let us look at it now. Now, if you between the two load points, we have also seen that external equilibrium and internal equilibrium has to be satisfied, right. So, between the 2 point loads, what are the external moment that it is created, that should be resisted by a couple consisting of compression in the top strut and tension in the tie. That means what does it say? If I take a free body diagram, this C and T has to be equal. So, we say that C is equal to T. Whatever C force that is coming in the top strut should be equal to the tension tie T. So, we can see here, this is one thing that we have established. What we have established here is C is equal to T. So, that you keep that in mind for this particular strut and tie configuration. Now, let us look at, we have to make sure that if a post tension reinforcement area is sufficient, that means whatever area times the stress will give me the force, and phi is your strength reduction factor, that is basically your capacity should be greater than or equal to your Nu, which is the tension force that is coming on the tie, right. So, that means the tie force can be carried out without any additional tensile strain, right. So, in this case, now I also have in this tie, when I look at this tie, I also have adjacent compressive struts and bearing nodes are allowed to sustain stresses up to strength reduction factor phi multiplied by 0.85 times F prime C, right. Now, again please note that F prime C here is always cylinder compressive strength, right. So, in India we use cube, and we know that the cube strength FCU is 1.25 times your F prime C, right, because of the aspect ratio, and we have studied in the material chapter, right. And 0.85 is typically because we are testing small cylinders, then when you are extrapolating it to a large member, then you know that you are going to have some defects. That defect is basically has to be taken into account, size effect. So, so we put this factor 0.85, right. So, we have discussed all those things in the material chapter, right. Now, we can see that we have to make sure that the adjacent compressive struts and bearing nodes are allowed to sustain stresses up to 0.85 F prime C into reduction factor, right. So, that means what we can say here is the permissible compressive stresses over the depth HA and over the DA are both 0.85 F prime C. So, that means in both the location the nodes are coming. So, I need to make sure that the nodes are subjected to maximum of phi into 0.85 F prime C. So, that means we can say that the C is equal to T. Then if that is the case, we can establish that the depth of your tension tie should be equal to your depth of your compression strut. So, that is what we are trying to establish. Now, equating that external and internal moment, for example, here I take a section XX like this. If I take the moment, now R1 into this distance. Now, what is this distance? We can see that from edge to the load point it is 3500. Now, I have to subtract 750 by 2, right. So, that is your R1 into the distance, which will give me external moment. So, that is one value. Now, it should be also equal to your internal moment. Now, what is internal moment? Internal moment is C into, here I have T. So, this is your thing. So, I take moment about, let us say, about this tension tie. So, we can say top strut force multiplied by the lever arm. So, now, what is the lever arm? Lever arm will be, in this case the lever arm is going to be basically 4000 minus half dA and half HA, right. That is your lever arm. Now, how about top strut force? Strut force we see permissible stress multiplied by the area of the strut. So, we can equate them like this, external moment is equal to internal moment, then you will find that R1 into this lever arm is equal to 0.85. Now, why do I take point? This is your phi factor, strength reduction factor, and cylinder strength I have taken 30 megapascal, and area of strut is, width is 500, this is your width of the beam, and this is your depth of your strut, right. So, width multiplied depth of the strut gives me the area of the strut, area multiplied by the stress will give me force, force multiplied by the lever arm will give me the internal moment. So, when you equate them, you get an expression that directly will give you a value for your dA. So, it works out to be 387.87 millimeter, and we are rounding off to the next integer, next possible round value, which is we are taking it as 400 millimeter. Right. So, that means basically at the end of the step we have found that dA, which is equal to HA, is equal to 400 millimeter. Right. So, now we have estimated what is the depth of the strut and the depth of your tension tie. Okay. Now, step 2, again we are continuing. You can see here, now that we have found the geometry, right, and we can calculate the angle alpha. Now, again this is simple trigonometry, right. So, if you do that, tan alpha is going to be basically from here to here, what is this distance is going to be 4000 minus half into this dA, which is 400, and half into HA, which is again 0.5 into 400. So, this distance is going to be 3600. Now, what is this distance? You see here, this distance is again 3500 minus half of 750. If you substitute that, alpha works out to be 49 degree. So, please, this should be always greater than 25 degrees. So, we are again satisfying that guideline that we have talked about in the beginning of the this module. Okay. Now, we have got, so now we have created the geometry. We have found out what is the depth of your compression strut and depth of your tension tie. We also calculated the angle alpha. Now, we can use the method of joint. We can consider the joint like this. So, where I have a reaction of 4000 kilonewton and I am having compression strut force which is coming from D, diagonal compression strut, and tension force is D. So, from your equilibrium condition, if you see D sin alpha should be equal to 4000. So, D works out to be 5300 kilonewton. If I take horizontal equilibrium, tension will be equal to D cos alpha, that works out to be tension is 3477 kilonewton. Now, of course, compression should be equal to tension. So, compression force at the top strut is equal to 3477 kilonewton again. Right. So, we have found out all the forces. Now, we form the geometry of the truss inside the deep beam, and we also ensure that it is satisfying the geometry requirement, and now we have also found out the forces. Now, once we have found out the forces, we need to check for your stresses and calculate the amount of reinforcement that is required. Now, let us look at it. Step 5 is to check for bearing stresses at supports. So, you can see here is 4000 kilonewton, and that you multiply by 1000 to get Newton, and your width here is 750 and width of your beam is 500. So, if you divide by that, you get a stress of 10.67 megapascal. And now, for different nodal zones, depending upon what type of nodal zone that you have, the code specifies allowable stress. So, for example, here always the strength reduction factor phi is taken as 0.7 for bearing calculations. If the nodal zone is bounded by compressive struts and bearing areas, the allowable stress is 0.85 times phi into F prime C. If you have an anchoring with one tension tie, it is 0.75 times phi into F prime C. If you have anchoring tension ties in more than one direction, it is 0.6 into reduction factor times F prime C. In this case, I have tension only in one side, so I have to take this particular scenario. So, if you see here, I take you see here nodal zone. So, the allowable stress for the nodal zone anchoring post tension tie is 0.85 times strength reduction factor times your F prime C. So, you work out to be 17.85 megapascal. So, which is greater than 10.61 megapascal. So, it is safe. Okay. So, both the cases it will be safe. Now, let us look at how to calculate the reinforcement for the tension tie. We have already calculated the tension tie as 3477 kilonewton. So, we know in tension area of steel multiplied by the effective pre-stress will give you should be greater than tension tie T. So, if you substitute effective pre-stress because we are taking 25% loss also. So, that is given there, right. So, you take 0.75 times 1860 as your and we also stretch it up to 75% of 1860. So, that is why this is your initial stretching force 0.75 times your FPK, that again you multiply by 0.75 because to account for your losses. So, that is why this 2.75s are there, and then 0.87 is basically your material safety factor. So, you see here you get a stress of about 910.2 megapascal. Now, force 3477, that divided by the stress will give me what are the area of precessing steel that is required. So, we can see that for each you put 4 PT tendons, each one of them will have 12 half-inch strands. Okay. So, 12 half-inch strands, you know that it is about 99.99 mm square, let us say, okay, half-inch strand, right. So, you can see that 12 strand will give me about 1200 mm square, and 4 of them, you are providing actually much higher than what it is actually required, right. So, that is what we are doing. So, the provided area is 4785, which is much greater than 3820 that is required. So, hence it is okay. Now, we have to check now that we have found out what is the reinforcement requirement, now I have to check whether the strut is having adequate capacity or not, right. So, let us look at the horizontal strut CC. Now, the permissible stress is 0.85 times strength reduction factor times F prime C. So, we take 0.85 times strength reduction factor is taken as 0.7 times F prime C is 30. So, 17.85, and the capacity of the strut is area of the strut, which is we have already calculated depth as 400 and it is acting over a width of 500. So, 400 into 500 into 17.85, that gives me a force of 3570 kilonewton, which is greater than 3477 kilonewton, therefore, it is okay, right. And now, we have done the top strut, now let us look at the diagonal strut capacity. So, here it is going to be little more involved. Now, I have to measure the width of this particular strut. So, let us look at it now. So, the permissible stress again remains 0.85 times 0.7 into 30, which is 17.85. Now, only thing is I have to calculate this area of this strut, right. This is the width. Now, what is that width? You see here using geometry, now that you calculated your alpha, you will find that the width of the strut, that inclined strut is going to be HA times cos alpha plus whatever that width of the support times sin alpha. So, if you substitute that, HA is 400, 400 into cos alpha, cos 49 plus width of the support, which is 750 times sin alpha, will give me that width of that strut. So, that width multiplied by the width of the beam itself, which is 500 times your 17.85, which is 7394 kilonewton, which is higher than your 5300 we calculated from your truss analysis, right. So, this is capacity, this is demand. So, you will find that the capacity is greater than demand. So, strut, inclined diagonal compression strut also is having adequate capacity. Now, we have to check the minimum reinforcement required for crack control. Now, let us look at it. The EC code, it requires uniformly distributed reinforcement in both vertical and horizontal direction, because you have now ties that are forming and struts forming. The strut also should not fail abruptly. So, the code requires that you need to have some minimum horizontal and vertical reinforcement, that works out to be about 0.15 percentage and 0.25 percentage. Okay. These are the minimum ratios that we have to put in vertical and horizontal direction. So, let us calculate that now. Now, let us use two numbers of 12 mm diameter bars. So, the area is 226 millimeter square. The spacing that is required, for example, for vertical is going to be 226 divided by 0.0015 multiplied by width, that gives me 300 mm spacing. Similarly, for the vertical reinforcement again, now it is going to be 226 divided by 0.0025, because it is 0.25 percentage for vertical reinforcement multiplied by the width will give me 180 spacing. So, that means I need to put two numbers of 12 mm bars at a spacing of 300 in the horizontal direction, and then in the vertical direction it should be less than 180 millimeter, right. So, we are providing horizontal reinforcement at 170 mm center to center and vertical reinforcement 300 mm center to center, right. So, this is for vertical, this is for horizontal, right. So, now final detailing if you put it. So, basically we are not showing horizontal vertical reinforcement in the vicinity of the post tension depth, only for clarity point of view, right. So, if you substitute, you have to put on either side two 12 mm bars. So, this is the spacing. So, horizontal spacing is we can say for black it is 170, for vertical it is 300 center to center, right. And we also have 4 PT ducts and tendons, with each tendon is having 12 numbers of half-inch strand, right. So, this is the configuration finally we coming up with for the post tension deep beam, which is subjected to 4000 kilonewton in the middle, 4000 kilonewtons in the middle. So, you can see this way using Strut-and-tie model I can quickly design a transfer girder.